All right, well, we've looked at implementing this little system for doing arithmetic on rational numbers as an example of this methodology of data abstraction. And that's a way of controlling complexity in large systems. But see, like procedure definition, and like all the ways we're going to talk about for controlling complexity, the real power of these things show up not when you sort of do these things in themselves. Like it's not such a great thing that we've done rational number arithmetic. It's that you can use these as building blocks for making more complicated things. Right, so it's no wonderful idea that you can just put two numbers together to form a pair. If that's all you ever wanted to do, there are tons of ways that you can do that. The real issue is, can you do that in such a way so that the things that you build become building blocks for doing something even more complex? So whenever someone shows you a method for controlling complexity, you should say, yeah, that's great, but what can I build with it? Okay. So for example, let me just run through another thing that's a lot like the rational number one. Suppose we would like to represent points in the plane. You sort of say, well, there's a point, and we're going to call that point P, and that point might have coordinates. Like this might be the point 1, 2. Its x-coordinate might be 1, and its y-coordinate might be 2. And then we'll make a little system for manipulating points in the plane. And again, we can do that. Here's a little example of that. Can represent vectors, the same as points in the plane, and we'll say, yep, there's a constructor called makeVector. MakeVector is going to take two coordinates, and here we can implement them if we like as pairs, but the important thing is that there's a constructor. And then given some vector P, we can find its x-coordinate, or we can get its y-coordinate. So there's a constructor and selectors for points in the plane. Well, given points in the plane, we might want to use them to build something. So for instance, we might want to talk about, we might have a point P and a point Q. So P might be the point 1, 2, and Q might be the point 2, 3. And we might want to talk about the line segment that starts at P and ends at Q. Right, and that might be the segment S. So we might want to build points in terms of numbers and segments in terms, we might want to build points or vectors in terms of numbers and segments in terms of vectors. So we can represent line segments in exactly the same way. Right, so the line segment from P to Q, we'll say there's a constructor make segment, and there's make-up names for the selectors, the starting point of the segment and the ending point of the segment. And again, we can implement a segment using const as a pair of points, and Carr and Kutter get out the 2 points that we put together to get the segment. Well, now having done that, we can have some operations on them. Right, like we could say, what's the midpoint of a line segment? So here's the midpoint of a line segment. That's going to be the point the points whose coordinates are the averages of the coordinates of the endpoints. If there's the midpoint. So to get the midpoint of a line segment S, we'll just say, grab the starting point of the segment, grab the ending point of the segment, and now make a vector, right? Make a point whose coordinates are the average of the x-coordinate of the first point and the x-coordinate of the second point, and whose y-coordinate is the average of the y-coordinates. Right, so there's an implementation of midpoint, and then similarly, we can build something like the length of a segment. Right, the length of a segment is a thing whose we use Pythagoras' rule. The length of the segment is the square root of dx squared plus dy squared. We'll say, to get the length of a line segment, well, we'll let dx be the difference of the x-coordinate of one endpoint and the x-coordinate of the other endpoint, and we'll let dy be the difference of the y-coordinates, and then we'll take the square root of the sum of the squares of dx and dy. That's what this says. Right, so there's an implementation of length. And again, what we built is a layered system. Right, we built a system which has, well, say up here there are segments. And then there's an abstraction barrier. Right? The abstraction barrier separates the implementation of segments from the implementation of vectors and points. And what that abstraction barrier is are the constructors and selectors. It's make segment and segment start and segment end. Right? And then there are vectors. And then vectors, in turn, are built on top of pairs and numbers. And so let's say pairs and numbers. And that has its own abstraction barrier, right, which is make vector and x coordinate and y coordinate. Right, so we have, again, a layered system, and you're starting to see that there are layers here. I ought to mention there's a very important thing that I kind of took for granted, and it's sort of so natural. On the other hand, it's a very important thing. Notice that in order to represent this segment S, I said this segment is a pair of points. And a point is a pair of numbers. And if I were going to draw the box and pointers structure for that, I would say, oh, the segment is, given those particular representations that I showed you, I'd say this segment S is a pair. And the first thing in the pair is a vector. And the vector is a pair of numbers. And that's this, that's P. And the other thing in the segment is Q, which is itself a pair of numbers. So I almost took it for granted when I said that Kant's allows you to put things together. But it's very easy to not appreciate that, because notice I can put some of the things I can put together can themselves be pairs. And let me introduce a word that I'll talk about more next time. It's one of my favorite words, called closure. And by closure, I mean that the means of combination in your system are such that when you put things together using them, like you make a pair, you can then put those together with the same means of combination. So I can have not only a pair of numbers, but I can have a pair of pairs. So for instance, making arrays in a language like Fortran is not a closed means of combination, because I can make an array of numbers, but I can't make an array of arrays. And one of the things that you should ask, one of your tests of quality for a means of combination that someone shows you is, gee, are the things you make closed under that means of combination? So it's not so, pairs would not be nearly so interesting if all I could do was make a pair of numbers. I couldn't build very much structure at all. Okay, well, we'll come back to that. I just wanted to mention it now. You'll hear a lot about closure later on. You can also see the potential for losing control of complexity as soon as you have a layered system if you don't use data abstraction. See, let's go back and look at this slide for length. See, length works, and it's a simple thing, because I can say, when I want to get this value, I can say, oh, that is the x coordinate of the first endpoint of the segment. And each of these things, each of these selectors, x coordinate and endpoint, stand for a decision choice whose details I don't have to look at. See, I could perfectly well, again, just like rational numbers I did before, I could say, oh, well, gee, a segment really is a pair of pairs. And the x-coordinate of the first endpoint of the segment really is the, well, what is it? It's the car of the segment. So I could perfectly well go and redefine length. I could say define the length of some segment S. And I could start off writing something like, well, we'll let dx be, well, what's got to be? It's got to be the difference of the two coordinates. So that's the difference of, the first one is the car of S subtracted from the x, the first one, the car of the other half of it, the coulter of S. Right, and then dy would be, well, let's see, I'd get the y coordinate, so it'd be the difference of the coulter of the car of S and the coulter of the coulter of S, sort of go on. And you can see that's much harder to read than the program I had before, but worse than that. I mean, suppose you'd gone and implemented length. You come. And then the next day George comes to you and said, I'm sorry, I changed my mind. I want to write points with the x-coordinate first. So you come back and you stare at this code and say, oh, gee, what was that? That was the car. So I have to change this to coulter, and this is coulter, and this now has to be car, and this has to be car. And you sort of do that, and then the next day George comes back and says, sorry, the guys designing the display would like lines to be painted in the opposite direction, so I have to write the endpoint first in the order, and then you come back and you stare at this code and say, gee, what was it? What was it talking about? Oh, yeah, well, I got to change this one to coulter, and this one becomes car, and this one becomes car, and this becomes coulter, and you go off and do that. And then the next day George comes back to you, I'm sorry, what I really meant is that the segments always have to be painted from left to right on the screen. And then you sort of, it's clear you just go and punch George in the mouth at that point. But right, but you see, as soon as we have, a 10-layer system, you see how that complexity immediately builds up to the point where even something like this gets out of control. Right? So again, the way we've gotten out of that is we've named that spirit. See, we've built a system where there is a thing, which is the representation choice for how you're going to talk about vectors. And choices about that representation are localized right there. They don't have their guts spilling over into things like how you compute the length or how you compute the midpoint. Right? And that's the real power of this system. Okay, we're explicit about them so that we have control over them. All right, questions?
What happens in a case where you don't want to be treating objects in terms of pairs? For instance, that in three-dimensional space, you'd have three coordinates, or even in the case where you have n-dimensional space.
Right.
What happens
okay.
there?
Well, this is a preview of what I'll say tomorrow. But the point is, once you have two things, you have as many things as you want, right? Because if I want to make three things, I could start making things like a pair whose first thing is 1 and whose second thing is another pair that, say, has 2 and 3 in it. And so on 100 things. I can nest them out of pairs. Here I made a pretty arbitrary decision about how to do it, and you can immediately see there are lots of ways to do that. We'll start talking about next time are conventions for how to do things like that. But notice that what this really depends on is I can make pairs of pairs. If all I could do was make pairs of numbers, I'd be stuck. Okay, let's break.